Okay, welcome everyone to Remi Coulon's second lecture on twisted Patterson-Sullivan measures. Remi, it's all yours.
Thank you very much. So let me remind you the goal of these lectures. So here's a statement I want to prove. So I take group G, which acts by isometries on a hyperbolic space, and I consider a subgroup, for instance, that assumes normal subgroup N of G. And then we can measure the size of its orbit with exponential growth rates. And we try to understand when the two groups, G and N, have the same size, so the exponential growth rates are the same. And it turns out that they are the same if only if the quotient is immutable. I told you there are two directions in this statement. So an easy one, which is if the quotient is immutable, then the growth rate should be the same. And a hard one, if the growth rate are the same, then the quotient should be immutable. And yesterday we covered the case when G is a free group and prove the hard direction, let's say. So what I want to do today is to focus on the easier direction, easier with some quotes, I'll tell you why. So saying if the quotient G mod N is immutable, then both G and N have the same exponential growth rate. And the reason why I want to go through this, there are two reasons. First, I think it is a beautiful proof. And second, that will be also a good way to introduce the main characters that will play a big role in the next lecture, which are Patterson-Sullivan measures. So even if you know what it is, I think it's good to go through again the details so that you will see how this works. And because later we are going to tweak that construction to make it a bit different. So let's begin. So here's the statement I want to prove, which is due, well, the proof I'm going to expose is due to Roblin. So we consider a group G which acts properly by isometries on a hyperbolic space and take a normal subgroup N. And we're going to show that if quotient G mod N is immutable, then G and N have the same growth rate. So for simplicity, I'm going to do everything with cat-1 spaces because it can be a bit burdensome to carry all the deltas when you work with Gromov hyperbolic spaces. So having cat-1 spaces would be fine. If you're not familiar with cat-1 spaces, just think you're working in the hyperbolic space Hn. That will be enough. And already in that case, the proof is very interesting. Okay, and some notation. So you'll see all the pictures I'm going to do are actually in H2, or looks like H2. So when you have the space H, well, Hn, H2, or journey cat-1 space, then you can consider the compactification, the visual compactification delta x of the space, and I rewrite x bar for the union of x and the boundary at infinity, which is a compact metric space. So typically, if x is the hyperbolic space, then your boundary is what you expect that a sphere of dimension 1 less, and when you combine the two, you get a closed ball, so which is a compact space. So to do that, we're going to go through construction of so-called Patterson-Sullivan measures. So how does it go? So I'm going to fix the base point once for all, O here. And then when you try to count stuff, it's very common to associate counting series to the stuff you want to count. And here, well, we use the Dirichlet form of the counting series, which is called the Poincare series. So you sum over, so I fix a subgroup H once for all as well, and I sum over all elements of H exponential minus S times the distance from O to HO. And depending on the value of S, this series may have a different behavior. It may converges or diverges. And so it's an exercise to see that that critical value where the behavior changes, is exactly the exponential growth rate of the subgroup H. So the series converges if S is very big, so if S is larger than H of H, and it diverges when S is super small, so when S is smaller than the growth rate. And just for having some vocabulary, because that's something we'll use later, so we a priori don't know what's happening exactly when S equals the exponential growth rate. So that's why we introduce two words. We say that the action of subgroup H is divergent, is a series diverge at the critical exponent, and it will be convergent otherwise. Typical example of divergent action is a proper compact action. So that's a good exercise if you want to manipulate that kind of things. Basically, you show that the cardinality of balls, when you have proper compact action, the cardinality of balls is submultiplicative. And then you use a variation of subadditivity lemma to show that the cardinality of balls grows at least like a given exponential, and that gives you the divergent at the critical exponent. Okay, so that was the Poincare series, but I'm interested in some measures. So here's the construction. So if I fix a point x in the space, and I forgot to say I fixed a parameter s, which is bigger than my growth rate, then I can consider a measure nu xs, which basically, if you look at this term here, so you take the Poincare series and you use the Poincare series to make a weighted sum of direct mass at the orbits of H. So you have the orbit of H in your space. You put a direct mass at each point. Somehow you want to do some an average of sort of a uniform measure on the space, on the orbits of the group. But since the orbit is infinite, you cannot do that. So you weight all the direct masses at the point in your orbit by the coefficient of the Poincare series. And then you rescale by the Poincare series to make sure that you have a finite measure. So especially if you take the point x to be the origin O, you can check directly that this measure you get is a probability measure. And then the space of probability measure on a compact set is compact. So up to passing to subsequence, you can make sure that this measure will converge for the weak star topology to another measure that I call nu x. So here I'm cheating a bit because, well, a priori, the subsequence you may have to take depend on the point x. So for each point x, we define a measure, and maybe for point x and point y, you would consider two different sequences to let them converge. So we'll see later that actually the same sequence will work for every point x, but that's for the next slide. So with this, you get a measure here, nu x, which is called the Patterson-Sullivan measure of the group H. And actually, it's easier to consider not just one measure, but consider the whole family of measure. So the family indexed by the point in your space x. And this family, we will call it a Patterson-Sullivan density of H. So it has remarkable properties. So let me state the main properties. So the first one is that the support of the measure is the boundary at infinity. So we started with measure where the support is inside the space, because that's our direct masses at points in the orbit, but the limit measure is supported on the boundary. So here I'm cheating a bit. If you follow exactly the contraction I gave you, this statement will only work if the group is divergent. If the group is convergent, you need to tweak a bit your Poincare series when you do the construction, but that will not make a big difference for my arguments. So I prefer to stick with that simplified version, but keep in mind that if the group is convergent, I'm cheating a bit here. So second property is the normalization. So nu O is a probability measure, purely abstract nonsense. You have a family of probability measure, you let it converge to something which is a probability measure, nothing complicated here. The third property, which is a reason why one reason why it's good to consider this family of measure indexed by X, is that you have some invariance property. So when you push the measure nu X by any element G in your subgroup H, you get the measure indexed by Gx. So this is also pure abstract nonsense. If you follow carefully the definition of this measure for nu Gx and nu X pushed by G, you write down what the definition is before taking the limit, take the limit, and you'll see it's completely abstract nonsense. There is nothing fancy here. And the last property of those measures are conformality. So what I mean is that if you take two different points, X and Y, the measure nu X, the measure indexed by the point X, is absolutely continuous with respect to the measure indexed by the point Y. And not only is it absolutely continuous, but you can also compute what is the Radon-Nikodym derivative. And this Radon-Nikodym derivative has a very simple form. It's exponential minus here the exponential growth rate times this function beta c, which is the Boozman cocycle at the point c. I never remember whether there's 2n or 1n for Boozman cocycles. So I'll explain briefly how these proofs work, because, well, first that would be a good way to remind you what's the Boozman cocycles, in case you forgot, and because we will see that proof again later in a different context. So let me take my notes where I am here. Okay, so conformality. So I draw the standard potato I do to represent my space X. And imagine I take a point C at infinity. So first, what is the Boozman cocycle? Well, I want to think that beta C of xy, the way I want to think of it is that the distance from X to C minus the distance from Y to C. But since C is at infinity, those distances here are infinite. So these does not really make sense. But that's really the way you should think about. So to be rigorous, to give a rigorous definition, the way we do is the following. So we consider a ray, a geodesic ray, gamma. So gamma would be a geodesic in your space that is converging to the point at infinity xi. And then you define the Boozman function beta xi of xy. Sorry, my xi are very horrible. As a limit when t goes to infinity of the distance from x to gamma of t minus the distance from y to gamma of t. So basically you do the formula above, but you approximate the point c by gamma of t and you let t goes to infinity. Exercise, the limit is well defined, and this Boozman cycle beta xc is 1 Lipschitz in the sense that if you compute beta of x and y, it's always smaller than distance between x and y. So that's 1 Lipschitz. That will be useful soon. Okay, so how do we do now how do we prove conformality? Well, imagine I pick a very small neighborhood here, U, that will be a neighborhood, oops, of the identity of the point xc. So I'm going to consider now a function f that is a function from x bar to r, which is supported in that neighborhood U. Okay, so now let's compute what is the integral of f against the measure d nu x before I go to the limit. So if you write down the definition, well, this is just 1 over p of s, the sum over all elements h, exponential minus s, distance from x to go, f of go. And I want to see that measure with the point y appearing. So I'm just going to do a slight change. So I do 1 over the Poincare series, same the sum over all elements in h, exponential minus. So here I want to have something which is exponential minus s, distance from y, this time to go, time f of go. So what I need to add here is, if I'm not mistaken, s times the distance from x to go minus the distance from y to go. So I'm just adding the terms that compensate for what I want. Okay, but now we're going to have a look at that term here. This, oops, that's not the one. Sorry. We're going to have a look at that particular term here, because here you see on this side I have exactly the measure of f against the integral of f against nu x, and here that part basically that the integral of f against the measure indexed by y. There's just this term in between which is kind of bothering. So if I go back to the picture, so imagine you have your point, your space here, the point C, and so have x and y somewhere here, and my neighborhood U there. So, well, maybe I should go back to the previous formula. So if you look here, this sum here is a priori over all element of H, but since I'm considering a function which is supported on the neighborhood U, it is 0 outside of this neighborhood U. So look now at this. It means that the point GO I'm considering are points around here. And then it's a property, that of Boozman functions, that if your neighborhood is sufficiently small, so GO is very close to the point C, then the distance from X to GO minus the distance from Y to GO, roughly speaking, this is the Boozman cocycle at C between X and Y. This is the intuition I gave you about this Boozman cocycle. So if you substitute that quantity here by the Boozman cocycle, you get a formula that looks like this, that the integral of f against d nu x at s. Well, roughly speaking, you may have a constant that will depend on s and on the neighborhood u of that you consider for the support of f, times the integral of f xi exponential minus the Boozman cocycle of xy d nu sy at xi. And if you take, if you let your, sorry, I forgot an s here, and I think I forgot it. No, it's okay. It's here in this computation here. So if you let s tends to the critical exponent hh, and you take your neighborhood of xi small, at the limit, this stuff will goes to 1. And this S here, I should take another color, this S here will tend to the growth rate of H. So what to get from this computation when S goes to HH is that the integral, well, I can directly write it with the radon-Nicodim derivative, is that the radon-Nicodim derivative of those two measures at the point xi is exactly exponential minus h Boozman cocycle at xi of xy. And you see, actually, if you look carefully at this proof, what it tells you, so it tells you various things. It tells you first that when we let this family of measures here converge as s approaches the growth rate, we choose this particular subsequence so that it converge for the point x. So this identity will tell you that the same subsequence will make the measure indexed by y converge as well. Then it tells you that nu x is absolutely continuous with respect to nu y, and then it allows you to compute the radon-Nicodim derivative as here. So that's the conformality. And a consequence which will be useful later is that because the Boozman cocycle is Lipschitz, you have a very rough comparison between nu x and nu y. So the measure nu x is always smaller than exponential h of h times the distance from x to y. That's the Lipschitz property for the Boozman cocycle times the measure nu y. Because this function is always bounded from above by these other one. So let me give you one more word of vocabulary. So I gave you the construction for the so-called Patterson-Sullivan density, which is a family of measures which turned out to satisfy the 4 points here. So, but we will consider other measures which satisfy those 4 points. So anything that satisfies the 4 points, I will call that an H, well, HH here, conformal H invariant density. And actually, if you have another thing that I'm lost in all my pens here. If you have another thing that the growth rate, if you have just a number, an arbitrary number h, we can even call that an HH, H conformal H invariant density. Any questions so far?
One quick question. So, are there essentially different things from the Patterson-Sullivan which are conformal densities?
No, these, what you mean well,
No,
the construction I gave are exactly the Patterson-Sullivan measures.
That's right. So what I'm saying is that there is some, are you saying something about a uniqueness statement also, that if you have a conformal density given by these axiomatics, then it has to be absolutely continuous with respect to the Patterson-Sullivan measure?
So that's true if your group is divergent.
Okay.
If it's convergent, you probably can have some jokes that's popped up somewhere.
Okay, thanks. Thank you.
But when the group is divergent, everything is fine. Yeah.
I have a question.
Sure.
So if you look at these measures nu x and let x vary along a geodesic to some point on the boundary, so you should think of these measures as converging to the delta measure at the boundary point, perhaps. Is that true?
So you can define a measure somehow index at the boundary, but the measure will not be, for instance, the direct mass at that point.
Okay.
I don't know if that's what the question is, because imagine that imagine your group X acts properly concompactly on the space X.
Mm-hmm.
So it means that it is really, because of the invariance.
Yeah.
No, now I'm confused. I don't want to say mistake. I don't want to say something wrong. So I'll think about it and I'll come back to it tomorrow.
All right.
Probably.
Thanks.
Yeah, because I don't want to say any mistake right now.
Yeah, sure. Thank you.
Yeah. Any other questions? Okay, so let's see how we can exploit those properties. And now I will do that for any conformal density, not necessarily the Patterson-Sullivan measures that I constructed. So one tool to do that, a very important tool, are called shadows. So what are they? So basically, again, you draw your favorite potato for the space X. And imagine you take now 2 points in the space. I have a point Y, I have a point X. And I'm going to consider a small ball around Y, which is a ball of radius R. And now I consider all the rays, the geodetic rays, that go from X, enter the ball, and hit the boundary somewhere. So, and I would look at all the points C I can obtain in this way. So basically, you'll get what's called the shadow of the ball centered at the Y of radius R, viewed from the point X. So this subset, which I drew here, this subset of the boundary, this is what we call the shadow center at Y, radius R, seen from the point X. So why are they important? Well, there is a way when you have a cat-1 space or a hyperbolic space to put a metric on the boundary. But the construction might be a bit tricky. But morally, the way you can think about it is that shadows plays a role of balls for that metric. And if you point to Y is very, very close, here is a point Y is very, very close to the boundary, you will get much, much, much smaller ball. So somehow the radius of the balls in the boundary, when you reformulate those in terms of shadow, is more or less related to the distance between X and Y. So you can think of those shadows as small balls, and that will be the correct picture. Okay, so main lemma that is used all the time when you work with Patterson-Sullivan measure is called the shadow lemma. So it gives a way to estimate the shadow of certain shadows when you have a conformal measure. So the statement is the following. So I assume here that H is a normal subgroup of G, and that would be a very important assumption. I'll stress where it plays a role. And I consider an H conformal invariant density on the boundary. And now I have a formula which, well, that's terrible color. I have a formula which allows me to estimate the measure for mu O of the shadow centered at GO view from O. And basically, the idea is that it behaves like exponential minus h times the distance from O to GO. So you have this term of both sides. And then you have also a certain weight, which is the total mass of mu of GO. So that's a very, very useful statement. And I'm going to explain you the proof. Again, because we will use a variation of it later. So I think it's a good warm-up to cover that case. Okay, so if I want to make that computation, well, let me first choose some notation, because otherwise it would be a pain to write everything down. So I would just write O for the shadow from O of the ball of radius of center at GO and radius R. And so what I'm interested is to understand what is the measure of this set. That's not. What is the measure of this set? So I'm just, for the moment, going to rewrite this using both conformality and invariance of the measure. So if I write mu O of this set, so what is it? That's, well, pure abstract non-set, that the characteristic function of O against d mu O. So far, nothing serious. But I want, if you remember the statement, here I have the measure at the point GO. So I want to introduce somehow the measure at the point GO. So to do that, I'm going to use a conformality, will give me the relation between the measure pointed at GO and the measure pointed at O. So this thing is the integral of, well, still the characteristic function of O C. And now I have the Radon-Nicodim derivative that arrive here. So H minus H, the Boozman function at C between, if I'm not mistaken, that would be O and GO. Integrated against the density pointed at GO. So here's just the conformality that I'm using. And I'm just going to rewrite this a bit, because I will like to use now the invariance. Well, not exactly, but I want to make a change of variable. So I can also say that this is a characteristic function of the set G inverse O computed at G inverse Xi. And the Boozman cocycle are also G invariants. So here I can write that this is a Boozman cocycle at G inverse Xi between the point between the point G inverse O and O, and still integrated it again against the same measure. And now I can make a change of variable. So I replace G inverse Xi by Xi, and I get the integral over of the characteristic function of G inverse O at Xi exponential minus H Boozman at Xi of G inverse O O times the difference is the measure I'm integrated here is G inverse star mu of GO. Does that make sense? So if I summarize, somehow I'm going to now renormalize this by the total mass of the measure at GO, that's the one term which appears in the shadow lemma. So if I compute 1 over the mass of the measure at GO times mu of the shadow, I get the integral of 1 over the characteristic function of G inverse O. How do you read that? Xi exponential minus H Guzman Xi between G inverse O and O times a measure. I'm going to write d mu. Let me check my note. D mu O of X of Xi, sorry, where I define mu X to be another measure built from mu, which is 1 over the total mass of mu at GO, G inverse star mu, sorry, here it's mu. We started from the measure mu of GX. And the important point is here that, oops, what I want, that measure here, well, you have one measure for every point X, and it's pure abstract nonsense to check that it is also a density, an H-conformal, H-invariant density. So it's not the original one, but still it has the same property. And here, if you want to prove that it is H-invariant, the fact that H is normal subgroup is absolutely crucial. If H is not a normal subgroup, you cannot prove that this one H-invariant. Okay, so how can we now exploit this rewriting that I did? So let me copy it again on the next slide. So, well, I should write it here. So, not what I want. Change color. 1 over the total mass of mu at GO. Mu O of O. This is what I want to compute. This is the integral of 1 of G inverse O Xi exponential minus H, the Guzman cocycle at Xi between G inverse O and O times, well, against another H invariant conformal density. Now let's look at the upper bound. So I want to find an upper bound for this stuff. So here we're going to use some easy geometry in the hyperbolic space. So imagine I have a point Xi here. So, well, maybe I should first write, so what is G inverse of O, this stuff? So O was a here, this will be the shadow viewed from G inverse O, centered at O with a radius R. So if I draw it in the picture, I have the point O here, and I have G inverse O, which is here. And I have a small ball around here, and I'm considering the shadow, so that will look something like that. So, and my shadow is somewhere, maybe I can change my color, is that thing. So this stuff is G inverse O. But now So you see that if you have a point in this shadow, what is the value of this Boozman cocycle here? What is the value of this stuff? Well, I told you the way to think of this Boozman cocycle is that the distance from Xi to G inverse O minus the distance from Xi to O. So here, this quantity, roughly speaking, it's about the distance from G inverse O to O, which is the distance from O to GO. Just because you are in the shadow. So roughly speaking, I'm checking a bit, but there are some multiplicative constants, which is why you have this C which comes in the shadow lemma, but 1 over the mass of mu GO mu O of the shadow, roughly speaking, that's exponential minus h, the distance from O to GO, well, time the integral of this, but this is just the measure for nu of G inverse O. So there is a constant here if you want to be precise. So in particular, that measure here is at most 1, because nu O will be a probability measure. So that gives you already the upper bound. So you have an upper bound for the measure of the shadow, which is exactly the one you want. And if you want a lower bound, you need to make sure that this set here this thing cannot have a super small measure. And I claim that it will never happen. So why is that? So let me do another picture. So imagine that for, you can find some G's, some R, so that this measure is arbitrarily small. So you have the point O. Imagine for some very big R. So you're considering a very big ball around the, oops, that's not the color I want if I want to be consistent with the previous picture. Imagine a very big ball around the space O, and you have some point G inverse O, which is very far from O, and you look at the corresponding shadow, so which will do something like that. So the corresponding shadow will be a very big subset like this. This is G inverse. Oops, I want a straight line. This is, yeah. This is G inverse of O. So if your statement is wrong, you can find families of G's that goes to infinity and radius that gets bigger and bigger, radius R get bigger and bigger, so that the light blue shadow on my picture has a measure which is arbitrarily small. So if you actually go to the limit, you will get another H-conformal, H-invariant density, but that will be supported on a single point, because those shadows will get bigger and bigger, and all the mass of your conformal density will be at a single point. But because of the invariance, if you have a density which is supported at a single point, then that point need be invariant under the group action. But if you started with the group H, which is non-elementary, it cannot fix a point on the boundary. So this will never happen, which means that this measure here these parts here, it is always bigger than some small epsilon if you choose the radius of the shadow correctly. And saying that this part is bigger than some epsilon is exactly the lower bound of the shadow lemma. So yeah, that's it. We proved the shadow lemma. Okay, so let's look at some consequence of the shadow lemma. That would be useful. So still consider a subgroup H, which is a normal subgroup of H. Still consider mu, which is an H conformal, H invariant density. And now I will look at a series which looks very much like the Poincare series here. But I added weights which are the total mass of mu at GO. So the important point to note is that compared to the Poincare series of the group H I started with when I was building the Patterson-Sullivan measure, we have a series here is indexed by all the elements of the ambient group, all the elements of G. But still the statement is that the critical exponent of this series is at most H. So if you started with a Patterson-Sullivan measure for the smaller group H, you get another series, but where the critical exponent is the growth rate of the smaller group, although the series is indexed by the entire ambient group. So then the strategy, whether the particularity, and the proof is also very geometric. So let me give you a sketch. So I'm going to consider a certain annulus. So I'm consider an annulus which are all the element G in the group G, so that distance from O to GO is between some number L and L plus delta L. So why? Because if you look at this series we are interested in, we are going to slice the sum into increasing annulus. So I want to understand what's happening on one single annulus. So the picture is the following. So you have your space, and you have an annulus somewhere here. Oops, that's big. So let's say you have an annulus which are all the points between distance L and L plus delta L. So, and you have some orbit, well, you cannot see here. So you have all the points in A are somewhere here. And now you can consider a subset of the boundary which correspond to the shadows of all these points in the annulus. So for each of these point in the annulus, so I should write, sorry. I should write some notation here. So I have the point O here, that's the GO, which corresponds to the point in the annulus. And for each point in the annulus, so I can look at the shadow of this point and also the shadow of this point, etc. I'll look at the shadow of all the points in the annulus. So maybe some points are in multiple shadows, but there is a property argument, since the action of the group is proper, that every point in the boundary is in at most, I don't know, 10 shadows, not more. Well, maybe 10 is 100, but there is a fixed number so that every point in the boundary is in at most 10 or 100 possible shadows. So, well, if I write this properly, so there exists an n such that every point in the boundary is in at most n shadows of the form O GOR for some G in my annulus. So now, well, what I can do is I can compute, well, I can give a lower estimate of the total mass of the boundary. This is 1 because, sorry, this was mu. My measure is mu. So this is probability measure, so the total mass is 1, and this would be at least 1 over n, the sum over all elements in my annulus of the mass of the shadow. But now from the shadow lemma, I can, yeah.
Quick question. So
sure.
n is dependent only on the delta n?
And it's just, the n comes from the fact that the action of the group G on the space is proper.
Yeah.
So
in terms of your constants, so does it depend on the inner radius of the annulus or only on the thickness?
No, it does not. It does not depend on the radius. The reason is because imagine you have one point the boundary that belongs to 2 shadows.
Yeah.
So the shadow of G10 and G20. That will force the distance between G10 and G20 to be at most twice the radius of your shadow.
Right. So it depends on your delta L, right?
What do you mean?
So you've written your annulus as L less than equal to DO less than equal to L plus some delta L, right? So there is some thickness of the annulus. Right?
So it will not depend. It will also not depend on the thickness of the oh yeah, sure, sorry, yeah. Yeah, that probably depends on the thickness of the annulus. Yeah.
Okay. Yeah. Thanks. Okay.
Yeah, that would depend on the thickness of the annulus. Yeah, you're right. But the important fact is that it does not depend on L.
Right.
Once the thickness is fixed.
Yeah.
So now if we go back to this computation, we can use lower bound of the shadow lemma, and that will tell us that basically this is at least a certain constant. I'm including the 1 over n in the constant times the sum of all elements in the annulus, the total mass of mu at GO, exponential minus h, the distance from O to GO, and which is roughly speaking, because I'm on the annulus, the sum from all the G in A of the total mass of GO exponential minus h times L. So which means if you consider the series I'm interested in, so I'm interested in at the sum of the total mass of mu at GO exponential minus s distance from O to GO. Well, this will be less, if you make the computation, than a certain constant exponential minus s minus h times L. This is what you get from your computation above. So you see that now if you're summing those, if you summing those terms here over L, when S is bigger than H, you just have a geometric series that converge. So, and when you sum over L, you'll get the original series you were interested in. So that tells you that this series here converges whenever S is larger than H, which is exactly what we want to say. It's always a nightmare to understand which direction the inequality goes when you work with a critical exponent. But what I'm claiming is that if this series converge anytime S is larger than H, then the critical exponent of this series is at most H. Does that make sense?
Did you use normality here for this?
So the normality, it's hidden in the shadow lemma. So the fact that I can apply the shadow lemma for shadows which are centered at a point GO with G in the ambient group, it uses the fact that H is normal subgroup. So if we go back to the shadow lemma, sorry, that was here. So the important point to notice here is, so I take G, which is in the ambient group. So I'm computing the shadow of GO for G in the ambient group. But I use a measure which is only H invariant. And if I want those two things to work together, I need H to be a normal subgroup. Otherwise, it's wrong. Okay, so let me now move to the proof of the easy direction. So now here, so we fix a normal subgroup N of G, and we consider the quotient Q, which is G mod N. The assumption is that that quotient group is amenable, and I want to prove that N and G, they both have the same exponent. So from N, you can construct a Patterson-Sullivan density, which is N invariant. But still, this Patterson-Sullivan density, you can act on it with the group G by pushing this measure by any element of G. So roughly speaking, you can think that, well, it's N invariant, you can act on G, so somehow you have an action of G mod N on this set. And because Q is amenable, you have a mean of Q. So one thing you'd like to do is, well, try to average those measures using a mean on Q. So this is the heuristic of the proof, but if you want to work out the detail, here's how this works. So the quotient Q is amenable. So another possible definition is that there exists Q invariant mean on the space of bounding function from Q to R. And now construct the Patterson-Sullivan density for the subgroup N. And we're going to associate to that a new H-conformal N invariant density. So how do we do that? So fix a function f, a continuous function on your boundary, a point x, and consider that map psi of fx, which associate to every element of quotient this big integral. So the first thing to observe is that this is well defined, because if I change u for here, if I change the u for some nu with n in n, because the family is n invariant, I will have the n that pops out and that compensate with this u inverse which I have here. So those two will cancel, and here the total mass also will not change, because when the total mass, if you push a measure, the total mass does not change. So this is indeed, this does not depend on the coset of n. So this is indeed a function from G mod n to R, right? And the other remark I want to do is that, oops, I erased too much. This function is a bounded function. So why is that? Well, if you compute what is this, so here, if I compute, for instance, the absolute value of fx at u. Maybe I should write the absolute value like this. So I can always put the absolute value inside the integral, and this will be at most, well, the L infinity norm of the function f times 1 over the mass of nu O. And actually, I don't need a 1 over because I can write what's the denominator, the numerator, sorry. Here at the top, I get the total mass of nu at ux, right? But because of the inequality I mentioned at the beginning, there is a very rough inequality between those two measures. So this is at most the L infinity norm of f times exponential h, well, hn here, the distance from ux to uo. But this is at most, now I can simplify by u, the infinity norm of f exponential h, the distance from x to o. So you see now these function psi fx, this is a function from q to r, which is a bounded function. The bound I have here does not depend on u. So if it's a bounded function, I can average it using my invariant mean. And it's exactly what we do next. So we define a new measure by saying that the integral of f against this measure is just the mean of this function. And again, this is some abstract nonsense that to check that it is still H-conformal and invariant density. So what did we get by averaging this measure? So there is a little trick here. We're going to use Jensen inequality, which is basically a generalization of concavity. So when you have convexity, when you have a convex function, the integral of a convex function is always larger than the function of the integral, if I'm not mistaken. So here, let's compute what is the total mass of this new measure I just defined here. So the total mass here, well, I can write it, this is the mean of this function psi 1 GO, but I'm going to write this function as exponential of logarithm of this function, so that I can use the Jensen inequality, which is just, again, some convexity, and this will be larger than the exponential applied to the mean of logarithm of 1 GO. Okay? So say differently, this total mass is larger than exponential key of G, where just by definition, key is this function. So just a way to rewrite this inequality. But now, one nice thing, so you can prove that also some abstract nonsense. You need to unwrap all the definition one after the others. But you can prove that this map key here is a homomorphism in the sense that key of G1, G2 is exactly key of G1 plus key of G2. So why is it a homomorphism? Well, you just go back to the definition involving this function psi. You write down what are those things. There is a logarithm will give you somehow the additivity, and then you use the fact that your mean is Q invariant. And the fact that the mean is Q invariant will directly leads you to this homomorphism identity. So I don't want to spend too much time writing computation, because at some point it's not very, I think, helpful to follow, but I encourage you to do the exercise, because that's really just what it is. You use the fact that M is Q invariant, and that gives you the fact that K is a homomorphism. So, well, where are we going now? So I computed some estimate of the total mass here of my new density. I had no particular good estimate of the, we started with the Patterson-Sullivan measure here, and I had no particular good estimate of the total mass of this measure. So we use this trick of averaging the measure, and now we get a new and invariant conformal density for which we have a certain estimate of that total mass. So why do we care about this estimate? Because that's exactly the one that was happening in the statement I mentioned before. So the next step will be to compute this sum, which is exactly the sum that we studied before, for which we know that the critical exponent of this series, this is exactly Hn. This was a statement I proved before. So, but now I can work out the computation. So first, this total mass, I'm going to replace it by exponential of K. And now what I can do is that I can say that, well, maybe I should write the intermediate step. So what I can say is that this stuff, this is also 1/2 of twice the same series. So that looks weird to write it twice. GO exponential of Kg plus, again, the same one. But the point here is now I will reindex the second sum. Instead of summing over all the elements of G, I will sum over all the inverses. So I will have an inverse here and an inverse here. Well, the thing is that the distance from O to GO, or the distance from O to G inverse O, that's the same. So if after I reindexed, I can always remove that G inverse. But now, remember, K was a morphism. And that's the important point. K is a morphism. So K of G inverse is minus. No, K of G inverse is minus G of K. So if you combine now those two sums together, you get this next one where you have still the exponential minus S distance from O to GO, but now you have the hyperbolic cosine of K of G. And you know that the hyperbolic cosine is always larger than 1. So that gives you an estimate, which here is the Poincare series of the entire group G. And that's the important point. So let's go back to the statement I mentioned previously. If S is larger than Hn, this series converges. So which means that this one here, well, not a good color, it also converges if S is larger than Hn. But we know what is the critical exponent of this Poincare series. It is exactly Hg. So that gives you directly this inequality. The critical exponent of n is at least the critical exponent of G. And since you always have this obvious inequality in the other direction, that gives you that two critical exponents of H and G, they are the same. And so that's the end of the easy directions. So we proved that if the quotient G mod n is amenable, then the critical exponent of n and the critical exponent of G have to be the same. So I want to make a small comment. So yesterday, Mahan asked me if the proof I gave for the so-called hard direction, when you, in the case of the free groups, whether it works for any subgroup, not necessarily a normal one, because we'll see later, I have not defined that, but there is a notion of amenability for a coset space G mod H when H is not a normal subgroup. And I said, yeah, that one works. Here, if you want to play the same game when n is not a normal subgroup, I don't know how to run that particular proof in the same context. Because the shadow lemma that I stated, it uses in a critical way the fact that n is a normal subgroup. And with my co-author, we have been trying to tweak that method in all possible ways, and we were not able to find a proof that will work if n is not a normal subgroup. I don't know whether it's impossible, whether there is some way we can fix that, but if you find a proof that will work when n is not normal, I will be super happy to hear about it. Here, that's some particularity n has to be, of the techniques, n has to be a normal subgroup. So if n is not a normal subgroup, there is another way we can work out this stuff. Maybe I can say a few words, which from my point of view is not completely, oh, yeah, let me find some fresh page. From my point of view, is not totally satisfactory, but imagine that, so if n is not normal, so imagine, for instance, that the action of G on X is co-compact. To make it easier, so what you can do is you can consider random walks on G or on G mod n, depending, how you compute the spectral radius, but which are where the measure, so with a measure mu, which is supported now not on the general n. So for each n, you have a measure supported of the Borel radius n in the group G. And then, so you can, as is in Keston criterion, you can compute what is the spectral radius of this thing, so that the lim sup when k goes to infinity of the kth root mu n star k of the subgroup n. And the idea that when you do the random walks with, where the measure is supported in larger and larger balls, it will look more and more like the growth, the growth rate of the group of the group G and the growth rate of the group N. And actually what you can prove is that this, if you take the log of K, this is roughly speaking Hn minus Hg. Sorry, is not, well, probably the best way. I'm going to write that to correct that. It's not very rigorous right now. Is so the fact I want to state is that the limit when n goes to infinity, basically that's the difference of the critical exponent. So this is what I'm saying. When you look at generating sets which are larger and larger balls, your random walks start to look like counting radius words or counting geodesic words. And so in this way, and this identity will work even if n is not co-compact. So in this way, n is not normal, sorry. So in this way, you get a relation between the critical exponent Hn and Hg and the spectral radius of the random walk. And you can use Keston criterion to say, well, if the group, if the quotients are minimal, this stuff will be always 0, so you get here an equality. I don't like very much this method because somehow, this is what I said, we are going back to the random walk, so we're using another dynamical system, which is not very natural to compute exponent growth rate, because the natural dynamical system would be more the geodesic flow, where you compute when you're counting words which are the shortest for the metric of the group. So it's not completely satisfactory, but I have no other proof for the moment when the subgroup is not normal. I guess I will stop here for today. Do you have any questions?
Let's thank speaker for a lovely talk. Right, so are there any questions at all?
So you're taking simple random walk with supported on this ball, is that right?
Yes.
And what's the idea of the proof of this statement? I mean,
it's a brute force counting.
Okay, thank you.
This is another reason why I don't like it. It's a brute force counting. And this is where, for instance, the fact that the action is co-compact is make it a bit easier, but it's a real brute force thing.
Thank you.
One question.
Sure.
So you've mentioned that the word co-amenability. So does that mean the Schreier graph is amenable?
Yeah. So I'll give you the precise definition tomorrow. But yeah, spoiler: the co-amenability. One possible definition is saying that the Schreier graph is amenable in the sense that the Chigrar constant is 0.
Okay.
Thank you. But like amenability, you have hundreds of equivalent definitions. So we will play a bit with some of them, but yeah, that's a possible definition.
Any further questions or thoughts?
So maybe I can just advertise what I'm going to do tomorrow and the day after.
Certainly.
So so tomorrow, so let's go back to. So here I gave you what I call the simplified version of the main theorem. So tomorrow I will give you the full version, the full statement, and discuss the new assumption and conclusion that we get, and maybe some other applications. And then I will explain the proof, which now involves the same kind of Patterson-Sullivan measure we worked, but which are twisted by a certain representation, in the same way we twisted operator by representation in the case of the free group. And we will see how those stuff work together, so how you compare the twisted measure with a regular measure and how it yields to the result. So that's the goal of the next 2 lectures.
Excellent, we're really looking forward. Great, so if there are no further questions, let's thank Remi again for a lovely talk. Okay, thanks again, Remi, that was really lovely. Thank you.
Bye-bye.